So the session is being recorded, and the first thing I'm going to do is share with you. I need to share with you my screen, applications screen. And I do this, and so in a moment, you should be looking at, Nicole, a thing that says unquiz. Is that where we are?
Yes.
Okay, I'm going to read this for you, and I'm going to give you 7 minutes to do this. And so let me see what time it is. Yeah, at 11:08, I'll call time. But this is an unquiz, and an unquiz is no risk to you, but it has all the benefits of having a quiz with none of the negatives. So anyway, here's what I'm asking you to do, and you really should be doing this without calculators. So determine the area of the region bounded by y equal 8 over x, y equal 2x, and x equal 4. And you shouldn't be using calculators, and take it seriously because it pays dividends thinking about these things. Okay, everybody, please go. Nicole, can you hear me again?
Yes.
All right, good, thank you. Okay, we're going to, declare this over, so everybody pause. And we're going to go over this. If you got the correct answer, congratulations. That means that you're in really good shape in this course. If you didn't get the right answer, this is only the second day in the course, and so, we'll see. And certainly you have an opportunity to learn something. The benefit of this is you're saying, oh, this might be the kind of question that Jim would ask, and what are the constraints, like no calculators and things like that. So that means you have to sketch the graph. So anyway, let's go over the solution to this. Okay, so here we go. Okay, so first thing that we're going to do is we need to graph these functions. So this is graph of y equal 8 over x. And this is the graph of y equal 2x. Now again, we're sketching these graphs. And this is the graph, this vertical line is the graph of x equal 4. So when I think about that, then clearly what the problem is asking us to do is to find this green area. And so we can tell clearly that the function that is on top here is y equal 2x, the blue function. And the function that is underground is the y equal 8 over x, which is the red function. And you do have to figure out what this point is here. The other point that you know is going to be x equal 4. Okay, so let's continue then. Okay, so we do need to find that intersection point correctly. So what we're going to do is we're going to set when is 8 over x equal to 2x. So I can multiply both sides by x, and I'll have 8 is equal to 2x squared, and then I divide both sides by 2, and get that x squared is 4, which means x is minus 2 or plus 2. Now, minus 2 doesn't make any sense in the problem, but plus 2 does. So that tells us that this value down here is plus 2. Okay, so, and we knew that the function, because of our graph of 2x was on top of the other one, so it is going to be, the area is going to be the integral from 2 to 4 of 2x minus the top function minus the bottom function, which is 8 over x dx. Now, when I integrate 2x, I get x squared. This minus sign is this minus sign, and I can pull the 8 through the integral. But then the integral of 1 over x dx, you should know, is the natural logarithm of the absolute value of x. And I'm going to be evaluating this at 4 and 2. So I plug in the numbers, and again, students should plug in the numbers. And what you get is that this is 12 minus 8 ln of 4 plus 8 ln of 2. Now there is some fancy stuff you could do here with logarithms, and I didn't do it, but you're not going to have calculators, so you're not going to plug it into calculators to get that. So you are to give me an exact answer, and I will check your exact answer to see if it is correct. So this is what you should have gotten for the answer is this expression right here, or something that is equivalent to that. Okay, so I'm going to count to 10, Mississippi, in case there are questions on this problem. Now, we're not in a classroom, and I have so many screens open you wouldn't believe it, so I can't, read everybody's chat questions. And in fact, what students do is they chat with each other, and they ask, "Oh, are you going to the ball game?" or something like that. And that's not what we're doing here. But anyway, I'm not looking at the chat, so I am going to ask you to go off mic and shout out if you can. Okay, so I'm starting counting right now, so please ask questions.
Could you explain again why 8 over x dx turns into 8 natural log of the absolute value of x?
Okay, well, one of the formulas that you learned, and I I'm actually writing this down on a piece of paper, but I'm sort of dictating to you, so I'm asking you to write what I'm saying. One of the things you learned is that the indefinite integral of 1 over x dx is equal to the natural logarithm of the absolute value of x plus c. Now, this is a fact that you learned in your calculus course, and some students will say, well, I don't remember that. Well, but it is taught in Math 2231. So this is an integration formula that you want to know. So the indefinite integral of 1 over x dx is equal to the natural logarithm of the absolute value of x plus c. So what I'm really doing here then is I'm applying that formula. So you see the minus sign is this minus sign. I can pull the 8 through the integral. So I'm integrating then from 2 to 4, 1 over x dx. So that gives me the natural logarithm of the absolute value of x times 8, and then I end up plugging numbers in. I hope that answered your question.
Yeah, you've got another question in the chat saying, if you haven't taken Calc 1 in a couple years, is there anything you would recommend to become more proficient?
You haven't taken Calc 1 and Calc 2?
No, this is a chat question saying that.
All right, so what I'm
they
going
haven't
to
taken
do
Calc 1 in
is
a
I'm
couple
going to
years.
stop sharing, and I'm going to go to the chat. And okay, so let's see, I need to go to Blackboard. Then I know this. Okay, so I'm going to call up the chats and see where did we, okay. Okay, so I'm going to answer all these chats because these students, maybe they don't have microphones or something. Okay, so one student says, am I supposed to answer the question on a random piece of paper, or I do the answer in another way? You try to work the problem, okay, is the answer to that. This is an unquiz, which means it gives you an idea of where are you in the course. If you didn't get the answer, you're probably behind in the course. Now, I'm not trying to be mean with that. This is only the second day of the class, but we do move fast. And so you're to try to work this on any kind of piece of paper. And if you say, oh, well, what I do is I do all of this in my head, then you should do it all in your head. Okay, then there's a question of where do we turn this in? This is another question that was on the chat. You do not turn in unquizzes, you grade them yourselves. I am giving you credit for taking an unquiz, but you see, this is something that has all the benefits of a quiz with none of the negatives. So you don't have to worry about getting a bad grade. You try to work it and you focus on learning something. But if you didn't get the right answer, that's telling you something. So you don't turn an unquiz in. And then someone answer, you don't, just do it on paper. Okay, and then someone says, okay. And then someone else says, it's a practice problem for yourself to grade. And that is true because you're trying to, figure out, well, gee, are you where you need to be? And then people say, thanks. And if I haven't taken Calc 1, now this wasn't if I haven't taken Calc 1, if I haven't taken Calc 1 in a couple of years, is there anywhere you would recommend to become more proficient? Now, and many people said, oh, look at Dr. Leonard's lectures, and other people said, look at Khan Academy, and other people said, oh, Susie Smith has a tutoring thing, or somebody else said different things. Well, I tell you that I have established an instructor level person to meet with you on a guided study group, and he sent you information about the guided study group. That's the very best way. I would recommend that, because I got to tell you, although Dr. Leonard is fine, my lectures are actually as good as Dr. Leonard's lectures. So I'd say, hey, pay attention to this lecture, and if you want to go back and review Calc 1, doing things with Jesse Hayes Carver or something would be like that. But I'm going to tell you that I think taking Calc 2 is almost a full-time job. And so you say, oh, I will go back and study Calc 1, you want to study that probably within the context of Calc 2. Okay, then somebody else says Khan Academy. Somebody else says, I think it's the same person giving all kinds of advice. Professor Leonard on YouTube. Professor Leonard's lectures are excellent, but he's doing these things on a chalkboard. He's just videotaping what he does in class. Somebody else says, oh, I like Organic Chemistry Tutor on YouTube because the Organic Chemistry Tutor teaches them some things. Somebody just did a frowny face. I don't know what that means. Then somebody said, appreciate it. Somebody said frowny face and YouTube videos for proficiency and extra problems. They go step by step through the syllabus. I don't know what the syllabus means there. And how do we get credit for turning in the end quiz if we don't turn it in? I just gave you credit for doing something. Now there will be LSAs. Okay, so I went through all of those chat questions. And again, one of the things I'm going to suggest just for the efficiency of running this, and of course, a number of you are just talking to each other and things like that. So that means you're not listening to me, which that's your choice too. Okay, so all right. So there we go. Let's see. Okay, so I'm going back then to where I was trying to be. So I'm going to go to back to sharing content. And now someone did ask a question about this this problem, which I think I answered. So that was good. And whenever somebody asks a question here, I do go back and start my count again. So this is for more questions on the problem that we were doing here. Okay, apparently there are no questions. Maybe they were all in the chats there, and I went over all of that. So I guess that's good. So we will.
Just one more, Professor.
Oh, another question. Go ahead.
Yeah, sorry, I kind of asked late. My apologies. You did say that the natural log of x was there because you have a fraction with a variable on the bottom. It just becomes natural log, right? When you have 1 over x.
Well, I'm going to repeat what I said because you didn't say exactly what I said. I'm not trying to be critical, but math is things, and some students will say, oh, they said if there's a fraction, it's always what's on the bottom. That's not true. Here is what is true. So, and I am going to ask you to write that down just because, you know, it is a short thing. This is what is true. The indefinite integral of 1 over u du is equal to the natural logarithm of the absolute value of u plus c. So that's something that you should have in your memory in order to do a problem like this. Did you catch what I said?
I think I did, Professor. You said the indefinite integral of 1 over u du is equal
to the natural logarithm of the absolute value of u plus a constant.
Okay.
I talked about Jesse Hayes Carver, and his sessions will be useful. I've also taught Calc 1, and I have lectures on Calc 1 as well that are 2231 at the College of DuPage. And so that person who was asking that chat question and things like that, I'd welcome you to come to my office hours if you want, and I can point you to those resources as well. Okay, I start my count again because I had a question. Okay, I hit 10. Now your questions are indeed always welcome, but we kind of finished that, so that is good. And now I'm going to go back to this little bit of an outline here. Now, I am opening up to if there are general questions, so I'm going to ask that. But there were students who actually asked me a question. When I finished working in the advising center last night at 7 o'clock, I did stop by the Learning Commons, and there was a student online asking a question that no one knew how to answer, and so they asked me, and I didn't know how to answer it. And it turns out it's one of my students, and they were asking, where is this video? Well, the videos are, and I'm answering this for you all now, the videos, whenever I hit, and Nicole, I think I hit record, and at the end of this, I'm going to hit stop recording. So what happens is Blackboard takes those videos and renders them from the analog format into, and encodes it into MP4. And that rendering takes a little while, but if you log into Blackboard Ultra, don't go to the class page, but go just to log into Blackboard Ultra. At the top left-hand corner, you will see 3 lines. And if you click on those 3 lines, it will say recordings. And so the recording's there. Now, my plan is to eventually upload these things, but it takes a long time to upload things to YouTube. So there's that. So those are immediately there for you. And another student asked, well, where are we in the book? We are done with section 5.6, and we're going to move on from there. We did an unquiz. I am just going to tell you that my plan for today is to lecture for more or less 75 minutes, and that means at around 12:15, we'll take a break, a 10-minute break, then we'll come back for another 50 minutes, but we're going to be covering new material. So I am going to pause just for a moment in case there's any general questions. I'll count to 10 Mississippi on this. So okay, no questions were posed. Again, your questions are always welcome. This was the unquiz that we did. Okay, this is what we're going to be doing today then. We're going to be talking about volumes today. Before we were talking about areas, and areas would come in square units like meters squared, but volumes are going to come in cubic units like meters cubed. And we're first going to be talking about the disk method and derivatives of, and derivative I mean just things that are similar to, not taking a derivative of the disk method. So the objectives here, I plan to talk about finding the volume of a solid of revolution using what we will call the disk method. Sometimes this is called the method of rings as well. We'll also talk about finding the volume of a solid of revolution using what is called the washer method, which is related to the rings method, except there's a hole in what you're doing. And then we will also talk about finding the volume of a solid with known cross sections. So those are the things that we're going to be covering today in our discussions. You've already learned that area is only one of the many applications of the definite integral. Another important application is its use in finding the volume of a 3-dimensional solid. So in this section, we're going to be studying a particular type of 3-dimensional solid. And this is a solid whose cross sections are similar to one another. The geometry is the same. And that will become clear when we look at the examples. And these are going to be called solids of revolution. So solids of revolution are used commonly in engineering and manufacturing. And some examples are axles, funnels, pills, bottles, and pistons. And in fact, if you look down here, you can see that these are things that people would manufacture. And you see, if you were to find and let's just suppose that this axis was going to be made of steel. If this axis is made of steel, an engineer can know the density of steel is mass per unit volume. And so if they know the volume of this thing, they can figure out how much steel is required to make this, and ultimately, in fact, the cost of this. So those of you who are interested in being mechanical engineers and designing things like this are going to be interested in this, and that's kind of the resulting product. In fact, some of you might be working for companies that do such things right now. Okay, so now we're going to start talking to this, and pretty soon we'll do an example. So when a region in the plane is resolved about a line. So you see I got a region, which is area, that's like meters squared, but we're revolving it about a line in three-dimensional space. There is a three-dimensional object form, and the resulting solid is called a solid of revolution. And the line that we're revolving about is called the axis of revolution. Now, the simplest such solid is a right circular cylinder or disk. So we're going to talk about that, which is formed by revolving a rectangle about an axis adjacent to one side of the rectangle. Now, let's look at a picture, and we are going to come back to that page, but here is the picture. So at the top, you see a rectangle. Now, the height of this rectangle is called capital R. And the reason we're using an R is because later on we're going to refer to that as a radius. So this is a capital R. And we also have a width that here we're calling W. So you see the area of this thing would be R, capital R times W. But we also talk about an axis of revolution. So what we're going to do is we're going to spin this rectangle around this axis. And what we get is we will have a cylinder when we do that. And we're spinning around the axis of revolution. Now, the symbol that we use for the axis of revolution is this little arrow here, which says, oh, I'm spinning this around that axis. So this is a useful notational kind of thing. And you see, if you take, and here's a drawing, if you take that rectangle and spin it around, you get a disk. Now, the top of the disk over here is going to be a circle, and the bottom of the disk is going to be a congruent circle to the top. And this width really is going to tell you how deep the right circular cylinder is. And you could almost think about this as being a can of tuna, perhaps, because a can of tuna, for reasons that we won't go into, but you have a big top on the can of tuna, and you also have a circular bottom on the can of tuna. But tuna's also, just the way the packaging usually comes, is that it's not very deep. So you could think about this as being a can of tuna that is laying on its side. Now, there is a volume of tuna that will fit in this, and the formula for the volume of a right circular cylinder is the area of a base, and by the way, the area of the top base and the area of the bottom base are the same, times the depth or the height of the cylinder. So you see, we're going to say the volume of a disk is pi. The volume of this disk is going to be pi. This is capital R squared times W. Now, everybody please understand that this is a volume because R might come in meters. So R squared is meters squared, and W could be also in meters, so we get meters cubed. So that's kind of the physics of what's happening here. I'm going to pause for a count of 5 in case people want to ask questions about this. Okay, your questions are always welcome, but we'll move on. Okay, now, and we did talk about this also last time because we talked about how integration is the accumulation of areas. So here we go. To see how to use the volume of a disk to find the volume of a general solid of revolution, consider a solid of revolution formed by revolving the plane area in this figure around. Okay, so you see here is we're taking this function here. It's the black function. It's like y equal f of x. and we're going from x equal a to x equal b. And now what we're doing is we're forming representative rectangles just to see, okay, so what happens when we do this? And then we're going to take a limit and eventually have an integral. So when you're looking at this, so I say, all right, I'm going to be drawing a representative slice here. I talked about how drawing these slices are useful, and you'll see that throughout today's lecture. So if we draw this slice this way, and notice it is perpendicular to what we're going to say is the axis of revolution, then we have the height of the rectangle is given by this. That's how far the function is from the axis of rotation. And the width down here is this little delta x. But notice that this rectangle is different from the rectangle you would draw over here, and it's different from the rectangle that you would draw over here. It's going to be a function of x. So capital R is going to be a function of x because it changes when you change x. Okay, so what we're going to be able to say then is, and we're just talking about this, the change in the volume by moving from here to here, delta x is going to be, and again, we're rotating this around this, and so we're going to get a disk. When we take this around, we will get a disk. And the disk is going to be like that can of tuna that we had. And so this is it is pi, capital R squared. Now, R squared does depend on x, and then it is times delta x. Now, please realize that the change in volume is going to be pi, which doesn't have any dimensions. It's going to be R squared, which has dimensions like meter squared, and delta x, which has dimensions of meter. So we get that. So we can do this, but we're also saying, oh, this is different every place we go to x. So what we're really doing is we're getting a representative disk, but as we move along this function, we get disks of different size. And so the volume is approximated by the sum of the volumes of these disks. So that means the volume is approximated by the sum of the volumes of those disks. Now we're using different values of x. So this would be the summation of r, it is pi, and then it is r, and this is x sub I whole squared times delta x. But we're going to say, oh, take the limit as n goes to infinity, as we do in calculus. Calculus is, after all, the study of limits. So the volume of the solid is equal to, you take this limit, but this limit really is an integral. So here's a formula that you have. So the volume of a solid is equal to pi times the integral from a to b of, and this is capital R of x squared dx. And schematically, this disk method looks like this. So we are going to take a known pre-calculus formula, and that's, we know the volume of disk is pi r squared w. But then we're going to draw these slices, and the representative slice says, okay, this rectangle would be pi capital R of xi whole squared times delta x. But then when I take the limit, adding up all these little slices, I get the integral, and this is the formula for a solid of revolution. So the volume is equal to pi, the integral from a to b. We'll talk about where a and b come from, and this is the this is capital R of x whole squared dx. Now this was a formula that we had when we were drawing a vertical slice. We can get the same thing if we draw a horizontal slice. So if we're drawing a vertical slice, here is the formula that I just did. By the way, if I'm drawing a vertical slice, that means that this is going to be dx, and that means this r of x must be a function of x, so that is r of x squared. So this is when we're revolving around the x-axis and we drew it perpendicular. Here is a situation where we're doing a horizontal slice because we're rotating it around the y-axis. Here we are perpendicular to the axis of revolution. Here we are perpendicular to the axis of revolution. This is something I typed in this morning because this is a bit of tradecraft. I think it's said here, but I want to make sure you understand. If we're doing what is called the disc or washer method, the slice is drawn perpendicular to the axis of revolution. Now you might be thinking, oh, that's not a big deal. I've taught this course many times. That is a big deal. This is helpful for students to pick up on this because we are going to be talking about other kinds of methods, and other methods are going to be called the shell method, where this doesn't happen this way. But in the disc or washer method, the slice is drawn perpendicular to the axis of revolution. So here are your two formulas. If it is dx, a horizontal axis of revolution, it's going to be pi times the integral from a to b r of x whole squared dx. And the volume here is going to be pi, and then this is going to be r of y because this had to be dy. Now, I could ask a question here, but I think what I'm going to do is I'm going to go ahead, and this is saying things I've really already said. So let's do a problem. And at the end of the problem, I am going to pause. And I'm going to count to 10 because people can ask questions about any of the theory or how we do this problem. Now, one of the things that's useful about unquizzes is an unquiz is a problem that I wrote. And so that's how I would write the problem and everything else. So you see, you're getting exposed to what kind of questions I would ask. Also, the examples that I do are written and constructed in a way that is exactly the way I would ask this question on a test. So you see, this is really useful if a student wanted to attend the lectures and study from the examples. Okay, so this is the first example we're going to do. And again, I'm going to pause. Your questions are always welcome, but they're really welcome at the end of this because I'm pausing and saying, okay, now we've done some work. Okay, so this example 1 says, find the volume of the solid formed by revolving the region bound by the graph of, it doesn't say y equals f of x, but it could because y is always f of x. So y equals f of x equal the square root of x. And the x-axis runs from 0 to pi. And we're rotating this or revolving this about the x-axis. Okay. So now what we're going to do, and by the way, this thing that I blacked out here, I blacked this out this morning because you see some students say, oh yeah, but you're going to draw a picture of this for us, aren't you? No, that's not the way we do things here. You have to sketch a picture of this yourself. So I erased this. This is C of figure or something like that. I want these examples to be really representative of the way I would ask a question. Okay. So this is the problem that we need to do. The first order of business is we want to sketch a graph of this. So you need to be able to sketch a graph of this without a calculator. Okay, so that means here's a picture. Now this is f of x equal the square root of x. Now we're going from 0 to pi, and that means we're in the first or second quadrant, and the sine function, the sine of x is always positive there. The sine starts at 0, it goes up to 1, and it goes back down to 0 here, but we're taking the square root. Now at pi over 2, where the sine of x is 1, it's going to be at the same place, but you'll notice that this is not exactly the shape of the sine because it's the square root of the sine x. But you say, okay, it's positive and it's going along like that. Now, what we're going to do is, and we're going to say this is the axis of revolution. And again, you should draw this little arrow because that helps you remember where you're doing the axis around. And then you're going to draw a slice. Now, this is where it's important for you to remember that in the disc or washer method, you draw your slice perpendicular to the axis of revolution. So that means here you're drawing a slice that is perpendicular to the x-axis. And when you draw that slice, you can tell, oh, I'm doing this problem dx. So this is the plane region that we have. Now, if you take this area and you rotate it around the x-axis, you get something that looks kind of like a football, and this is the solid of revolution. Again, you're rotating an area, so that's going to be meters squared, but you're also doing the delta x or dx that gives you a volume. And so what happens is you're integrating these volumes in the limit. So that's what the pictures look like. And this is probably the most critical picture for you to draw. Then you say, okay, so what is my radius? Let me go back here. And you see if you're spinning this around, and here's your representative rectangle, so you see that r of x goes from y equals 0 up to this point, which is r of x. So you see this is the radius for that rectangle. Over here, the radius would be something different. Over here is something different. But we're integrating, we're taking the limit, so all those things are fine, and we get the football-shaped kind of thing. Okay, so the capital R of x in our problem is the square root of sine x. But now you can apply the formula, and some students ask, oh, we'll have a formula sheet. No, you won't. The math department does not allow formula sheets here at the College of DuPage, so you want to know this. So this is the formula for the disk method that we derived before. So this is the volume is equal to pi. Now the pi is outside the integral because you can always pull a constant through there, and this is just a piece of tradecraft. But as a practicing mathematician, I will pull that pi out 10 times out of 10. And then I integrate from a to b. This is capital R of x. And by the way, a student this morning asked, well, can I just call it little r of x? Well, on one hand, you could call it anything, but we're going to be talking about things where we have outer radii and inner radii. So I think it's useful for you to think about this as big R being the outer radius. But it is a function of x, and this is dx because we looked at how we drew the representative rectangle that told us we were integrating dx. So now we can substitute everything in. Pi is pi. The problem told us that we were going from 0 to pi. When I square r of x, this is r of x. So when I square the square root of sine x, I just get sine x. So now this is pi, the integral from 0 to pi, and this is sine of x dx. And then you know, and again, this is one of the many formulas. It's almost like the logarithm formula. You have to know this, that the antiderivative of sine of x. And by the way, the student who was asking about catching up, I think I can give you some good advice if you stop by the stop by my office hours or something, or go to Jesse Hayes Carver. He can help you equally as well. So anyway, the antiderivative of sine is, you are supposed to know from Calc 1 that this is the negative of the cosine of x. So this is pi times the negative cosine of x, but then I'm going to be evaluating this at the endpoint. Now you have to be careful about this SIG in here. First of all, it has to be a negative there, but then the cosine of pi, which is the top point, is -1. So that is minus a -1, which is 1. And then there's a minus sign in the fundamental theorem of calculus, and then you're plugging in 0 into the whole thing. Well, the cosine of 0 is 1, so this is -1, but it's minus a -1. So we end up with pi, and this is minus a -1, minus a -1. 1 and 1 is 2, so this is 2 pi. So the correct answer to this problem would be 2 pi, and we had a number of steps. It started with graphing it. We drew our slice, we set up the integral, and then we had to calculate the integral. Now I'm going to pause for, this is our first real example, and I know we kind of rushed through some things. So this is a very important interval for you to ask questions. So I'm going to count to 10, and I'm going to ask you to shout out so I don't have to change channels and go and look in a chat box and things like that. But if you can't do that, you could put there. Hey, Nicole, I have a question for you.
Yeah.
Can you see the chat box yourself?
I can see like when a chat pops up, but I don't know how to access.
Okay, well that's what I'm going to ask you to do. In addition to being my deputy, I just increased the thing. But let me know when there's chats popping up, and we'll go see if there's anything happening. Now, if people are just saying hi to each other, we won't spend a lot of time on that. But if people are asking content questions that way, although I really encourage you to it's more efficient if you can just go on mic and shout that out. Nicole, are you okay with that increased responsibility?
Yeah.
Okay, great. And Nicole, again, I truly appreciate this. Okay, so I'm starting my count now, and I'm really asking for your questions. Okay, your sister class had a lot more questions, but maybe I did a better job explaining it because of that. Okay, so the expectation is that you know how to do a problem like this. So we will continue then. Okay, so this is example 2. And again, I crossed out some stuff here because you see part of what I expect you to be able to do is to sketch this yourself. Okay, so I'm reading the problem then. Find the volume of the solid formed by revolving the region bounded by the graphs of y equals f of x is equal to 2 minus x squared, and g of x equal 1 about the line y equal 1. Now, the big difference in this problem from the one that we did, I guess there are 2 big differences. One is we're talking about the region bounded by the graph of 2 curves. And we're also talking about revolving it about a different line, not y equals 0, which is the x-axis. We're revolving it around y equal 1. Okay, so this is what we're going to do, and I tried to give you time to get a sense of this and things like that. So the first thing we're going to do is draw the graph. And so let's look at the graph. Now, here is an x, y axis. So here is the x-axis, and here is the y-axis. But we are not revolving it around the x-axis. The axis of revolution is y equal 1. So if we go up 1 on the y-axis, this is the line y equal 1. So you see, this is where we put this little circle thing because that's the one that we're rotating it around. And it was supposed to be the area between, it's going to be the region between y equal f of x is equal to 2 minus x squared. Now you see y equal minus x squared is a frowning parabola, so we just move it up 2 units and we get there. So this black curve is what we get for that. But we wanted to rotate the plane region that was between that curve and y equal 1. So you see, it's this blue region that we're going to do. Now we are going to draw a representative rectangle. The representative slice is going to be perpendicular to the axis of revolution because we're using the disk method. So we take this and we draw this perpendicular to the axis of revolution. So this is perpendicular to this. So these are the rectangles. Now these do change as we go along, but that's what we have. But what is the r? Well, the r is the distance that we get between the axis of revolution in this. So you see the r is from y equal 1, this line, to the function. So this is capital R of x. Now this is still delta x. And whenever we take this around, so you see we're holding this fixed and we're whopping this around, and it looks like a superinflated football this time. And again, see, we're not going around the x-axis, we're going around y equal 1. So you see the football is sitting at the origin 0, 0. Okay, so again, it's important that you can draw the picture. It's important that you understand the picture. And whenever we reach a point where we have an answer, I'm going to ask if there's questions, and you can go all the way back to this. So I encourage your questions always, but we're going to use this then to do the calculations. Oops, that's not here. I'm going to talk about that a little bit later. So I need to go back and talk about that. All right, so, and in fact, I'm going to go back to first. Okay, I go here. Now you see, we also need to know, because what I'm rotating is between this point and this point. So I need to know what are these points of intersection like we studied before. So the black picture is f of x equal 2 minus x squared. The g of x picture that is just here is y equal 1. And so that's what we're doing. So we need to know, when do these intersect? So I need to know this point and this point to know the bounds of the integration. So let's talk about that. So what we're going to do is we're going to equate f of x and g of x. And so if we equate f of x and g of x, we can realize that that's going to tell us where the two graphs intersect. So when we set f of x equal to g of x, we're saying that this one is equal to 1. So when we solve that, that means this is equal to 0. And that means, or excuse me, that means that this is, okay, so this is 1 minus x squared. And so when is 1 minus x squared equal to 0? And that means we're integrating between -1 and 1. And the r of x, going back to the picture again, the r of x is going to be the distance between 2 minus x squared and 1. So if you take 2 minus x squared minus 1, you get 2 minus 1 is 1 minus x squared. So you see that's also going to be okay. All right, I need to find out where we are. I think we were example 2. Yeah, this is the one we're doing. Okay, and I was here. And so what we're going to do is then we're going to use our formula that v is equal to pi times the integral from a to b. This is capital R of x. This is the radius of the disk in the disk method, whole squared dx. But we know that r of x was 2 minus x squared minus 1, which is 1 minus x squared. So I'm putting 1 minus x squared whole squared here, and then this is dx. So this is the correct integral, and now we have to calculate this integral. Now, some students might be thinking that you can use substitution on this. I'm going to tell you you can't, because if you let u equal 1 minus 2x squared, du is going to be minus 2x dx, and there is no factor of x here. So the only way to do this calculation from the calculus 1 is you have to expand this. So we're going to take 1 minus x squared times 1 minus x squared. Now when I do that, we're doing algebra first. This is going to be 1 minus 2x squared plus x to the 4th, and this is dx. So now we're going to integrate this. Now the pi just sits out here, and we'll do the integrals term by term. So when you integrate 1 is the same thing as x to the 0. So we add 1 to the exponent, divide by the new exponent, that's going to be x. And then this minus 2 is, I would pull it out of the integral, doing it term by term. And so we're integrating x squared. So we add 1 to the exponent, we get x cubed divided by the new exponent, so it's x cubed over 3, but it was times the 2. Plus, and then we go to this one, the antiderivative of x to the 4th is x to the 5th, add 1 to the exponent, divide by the new exponent, you get that. And then we're going to go 1 and minus 1, use the fundamental theorem of calculus, and we have to plug these numbers in and actually do the calculation. And you will be doing these calculations without calculators, because that is the College of DuPage Math Department rule. So you have the pi sitting out here. You do this calculation without a calculator, and you get 16 over 15. And the answer to this problem is 16 over 15 pi. So you see pi comes up a lot in these kinds of problems. Okay, now that really finishes this problem. So I'm going to pause. I'm going to count to 10, Mississippi, and I'm going to ask, I'm really soliciting your questions. And Nicole is watching the chat box in case some of you are, asking your questions via chat. But I'm really encouraging you to maybe speak out if your technology is working. So anyway, I'm starting a count. I'm going to go to 10, Mississippi. And your questions could come from anywhere on this.
Could you explain how you expanded from 1 minus x squared to 1 minus x squared, or 2x squared plus x to the 4th?
Yes, I can. I'm going to try again, and I failed last time because I didn't. Okay, so I'm going to, first of all, I think I already stopped sharing. So now what I'm going to do is share the blank blackboard. Okay, so it is here. Now the thing that I didn't do is, I guess what I'm going to do is I'm just going to type this because I didn't draw it well last time. Okay, so this is parentheses 1, and that was minus x squared. I need to retype that, so that is 1 minus x, and then this is whole squared. I'm going to do the squared that way just to be convenient. But you see, this was squared, so that is it times itself. Like 2 squared is 2 times 2. So 1 minus x squared whole squared is 1 minus x times 1 minus x. So you can't see what I'm doing?
No.
Okay, let me, I was trying to share the.
Oh, there we see something.
You can see it now. It takes a few seconds. There's a few seconds delay.
Okay, so that is some. Okay, so that was some seconds. But now I guess you can see this now. And thank you whoever was shouting that out.
Yeah.
Okay, so this is 1 minus, this is x squared again. So you see 1 minus x whole squared is this. But now I'm going to FOIL this. Okay, so I take the first times the first. So 1 times 1 is. I guess I have to do it this way. So 1 times 1 is 1. And then I take 1 times minus x squared, which is going to be minus x squared. So I finish distributing the 1, then I go to this one. So then I'm going to be distributing this one. So this is minus x squared times 1. Well, that is minus x squared. Okay, and then I'm going to take minus x squared times minus x squared. Well, minus times a minus is a plus. Okay, and so this is going to be, that was my phone beeping. Okay, this is going to be a plus x to the 4th. Okay, and now you can see what I was typing. Sometimes these blackboards, you have to finish typing before they'll do some things. Now, I'm not really quite finished yet, though, so I'm going to make one more line, because you see I got minus x squared and minus x squared. It says minus 2x squared. So this is 1 minus, this is going to be 2x squared, because you got 2 of them, and this is plus x to the 4th power. So I hope that answered whoever asked that question. Did I answer your question where that came from?
Yes, thank you.
Okay, good. And whenever a student asks a question, I always start my count over again, because this could have stimulated some other things. Now I'm going back to sharing the application. Yeah, and Abraham told people in the chat that, addition is commutative, so you could have done that in any order you wanted. That could have been x to the fourth minus 2x squared, and so on and so forth. Okay, so let's go. Okay, so I need to go back to the, and some people are leaving the session. We will be taking a break in a bit, but if you have to leave, you have to leave. Okay, so let's see. I need to go back to the application screen then, and so I'll be sharing this, and I will be throwing up the PowerPoint slide yet again. Okay, and I need to hide that so you can see everything. Okay, I'm starting my count again. Okay, your questions are always welcome, but apparently that was the only question. I guess I did this the order in which it showed up here. Okay, so anyway, that is good. Now what we're going to do is we're going to go into something different, and it's not really totally different. I do know what time it is. We're going to be taking a break in about 10 minutes, but we're going to be talking now about something that's called a washer. And a washer is a hardware piece that is like a disk, but it has a hole in the middle. And if you understand about washers, that's fine. Some students like to think about donuts, that's fine. But we're going to talk about the washer method. So here we go. The disk method can be extended to cover solids of revolution with holes by replacing the representative disk with a representative washer. The washer is formed by revolving a rectangle about an axis, and I'm going to show you a picture of this. But in fact, let's go to the picture right away, and we'll come back to this slide. Okay, so here is what's happening. Now, your axis of revolution is this one right here. But your rectangle is floating above the axis of revolution. It's not sitting on the axis of revolution like it was in many of the earlier problems. And it's floating at a height that is called little r above the axis of revolution. So that's what we have. But we still have a big R, which is the distance from the axis of revolution up here. So we have an outer radius and an inner radius. Now think about holding this and rotating this around that axis of revolution. Yes, if you get a disk with a hole in it. And so what's going to happen is this is what's like a washer because it's got a hole in it. And so it's important that you realize, and so here is the axis of revolution. The big R is the outer radius. The little r is the little radius. And if you think about this for a while, what's going to happen with the formula is it's going to be the big disk with a hole filled in minus the little disk with a hole taken out. And that's the equation that we have on the previous slide. So you see the volume of the washer then is going to be pi r squared w. That's the volume of the disk, the whole solid disk, the outer disk. But what you're going to be doing is you're going to be subtracting pi times little r squared w. So this is the washer formula. And that means this is how it works. So the volume is going to be pi, and the pi is times the entire integral. This is the integral from a to b. This is big R of x whole squared minus little r of x whole squared. It's the outer radius squared minus the inner radius squared, and the whole thing is pi. Now here's another example that I'm showing you here. And so what we have here is we're going to take this little piece of stuff. Notice that I'm rotating this around this axis of revolution. It is a horizontal axis of revolution. And notice that I'm striking my slice perpendicular to the axis of revolution. So I'm taking this around there. And so you could think about maybe your eye being over here. But if you think about that, you see there is space between here. So what you get is, when you take this around, you get a solid of a revolution with a hole in it. And here is an important note, but the formula says it all. Note that the integral involving the inner radius represents the volume of the hole. And this is being subtracted from the integral involving the outer radius. So let's do a problem of this. And here is a problem. And by the way, you guys actually, I'm remembering that you guys actually did something similar to this as the last example we did in yesterday's lecture. But anyway, this is find the volume of the solid formed by revolving the region bounded by the graphs of y equal the square root of x. That should be familiar from last time. And y equal x squared. And we're rotating these about the x-axis. And again, I cross this out because it says OS shown in a figure. I'm not giving you the figure. You are to graph them yourself. But you did that last time. So we're going to wade in and do this. So the first order of business is drawing a graph, sketching a graph. So here we sketch a graph. Now this is the graph that we talked about yesterday. And we actually found that these two things intersected at 1, 1. And so we had y equal x squared and y equal square root of x. And we said they intersected at 0, 0, and 1, 0. But now what we're going to do is we're rotating this about the x-axis. The curve that's on top is y equal the square root of x. The curve that's on the bottom is y equal x squared. So we're rotating around here. You can think about your eye being over here and you're watching this. And this is your representative rectangle, again, perpendicular to the axis of revolution. Okay, so the solid that you get whenever you do this looks like this. But the important thing computationally is you're going to be using the washer formula for this. Now the curve that's on top is the square root of x. The curve that is on bottom is x squared. Okay, so here we go. So the outer radius is this one because it's furthest away from the axis of revolution. The inner radius here is little r of x is x squared. I'm going to integrate this between 0 and 1. Okay, so here we go with that. So the volume is equal to pi is sitting there, the integral between the points, which are going to be 0 and 1. You take the outer radius whole squared minus the inner radius whole squared dx, because this is the washer method. This is the formula that we've learned, and this is what we're going to apply. So now we're just going to substitute things in and do the calculation. So this is pi. This is the integral from 0 to 1. Now this is going to be the square root of x whole squared. And the square root of x whole squared is x. This minus sign is that minus sign is this minus sign as well. So it's minus, and then the inner radius is r squared. But this is r squared whole squared. Now r squared squared, this is properties of exponents, is r to the 4th. So I'm going to be integrating pi. This is the integral from 0 to 1. This is going to be x minus, this is x to the 4th, and this is dx. So this is pi. And now I have to integrate this. So I add 1 to the exponent, divide by the new exponent, minus this minus sign is that minus sign. And x to the 4th, I add 1 to the exponent, divide by the new exponent. I get x to the 5th over 5. I have to plug in these values. Now plugging in 0 is easy because that's going to be 0. But when I plug in 1, I'm going to have 1/2 minus 1/5, which is going to be 3 over 10. And I multiply by pi. So the answer is 3 over 10 pi. Okay. Now I am going to entertain questions, and I always watch the clock, and so we're getting near a break. So I am going to ask for questions after the break, but I'm going to do something in the 3 minutes to use it of value. And one of the students in your sister class said, well, I don't understand about LSAs. What are they? And so to answer his question, I said, okay, I will give you an LSA just to start with. So I didn't have this prepared, but I did give it to him. So here is your first LSA. And so this is an LSA, low stakes assessment. That means you can get help, you can talk to Jesse Hayes Carver, but the work should be your own because this is, certainly a test quality question. So this is going to be due before midnight on June 19th. And Jesse Hayes Carver or I will tell you how to upload this to Blackboard and things like that. And if you say, oh my gosh, I can't get it done. I can't get it done until 12:30. What do I do? I'm not deducting you for that because my number one thing isn't grading you harshly. My number one thing is teaching you a course that's a good course. So anyway, this is your first LSA. He asked for it. And so this is what the LSA is then. It's due before midnight on June 19th. This is consider this function y equals f of x is equal to the absolute value of 2 over 3x cubed minus x squared minus 11 over 3x plus 2. And again, it's the absolute value. So I ask you to do two things in this low stakes assessment. Graph this function and find the area of the region between this curve, the line x equals 0, and the line x equal 4. So that's an example of a low stakes assessment. And again, he asked for this, so I answered his question by giving this. So yours is due there as well. Now, again, after the break, I'm going to count to 10 Mississippi. We'll talk about this. And I want to hear any questions you have about the washer method after the break. Now, it's exactly 12:15, so I'm going to start talking again at 12:25. Okay, so we're reconvening at 12:25. You're on break now. I was teaching a calculus 2 section. That's why I couldn't. Okay, what's the Nicole, can you hear me?
Yes.
Great, thank you. Someone made a suggestion about how I can watch the chat box. It turned out, as at least the way I was showing the PowerPoint slides, I can't do that, but I'll work on that. And thank you for the suggestion. And I'll see if I can figure that out. But I tried something simple and it didn't work. Okay, so what I'm going to do, I am going to be sharing my applications screen with you. And Nicole, we should be looking at, some PowerPoint slides, except that's not the one I want. So I'm going to go back and find the one I want. I think, and I have to hide the sharing button, and we have this one. Okay, so what we're doing then is I'm pausing here to see if any students have any questions about this important washer method example. So I'm going to count to 10 to give you an opportunity to voice your questions. And I guess Nicole is watching the chat box in case students are writing chat questions that are relevant to this, that I should be aware of. Okay, so I'm starting my count right now.
This isn't about the problem. This is about the LSA.
Okay.
Where do we turn it in exactly once we finish it?
I'm sorry, you weren't. I could not understand what you just said, but please say it again.
Once we are finished with the LSA, where do we turn it in?
Okay, Jesse Hayes Carver will create a place for you to upload PDFs, or I will create it. So what you should do is take a picture of this, and you'll be uploading it to Blackboard. Okay? Now, it's not there yet, but watch your announcements, watch your emails, and you'll find a place.
Okay, thank you.
Okay. And I'm going to find the problem we just did. And I'm starting my count again.
Could you go back to the graph of this problem?
Yes. Is this the picture you want?
Yes.
Okay, great.
So based on the graph, that's how we know that we want to be integrating this from 0 to 1, correct?
Well, I'm going to say yes, but your class did a problem like this yesterday, where, and I think it was the very last example that we did, where you were supposed to go and say, what was the area? Now, it was a different problem, but what was the area between these two things? And so, and maybe I'm not remembering, but anyway, I think I am remembering correctly, but that doesn't matter. So you have to figure out, where does y equal the square root of x intersect y equal x squared? And you find that by setting x squared equal the square root of x, and you square both sides, and you end up solving it. And you find out that, that will either happen at 0, or will that happen at x equal 1. So, I mean, I guess I'm agreeing with you, but I want to make sure that I'm answering the question. So we had to do a step to figure out this goes from 0 to 1. Now, it did come from the graph, but just sketching the graph, you may or may not know that this is 0, 0, and this is 1, 0. Did I answer your question?
I'm still a little confused. I may have just not understood completely, but what was the step that we had to take to make sure it was going from 0 to 1?
Okay. Now, I'm going to do this step because I did a little bit of experimenting. And so what I'm going to do is I'm going to go and I'm going to do the step that I just talked about. Okay, so I am going to go to here, and I'm going to stop sharing, and I'm going to share a blank whiteboard. Nicole, you can see a blank whiteboard?
Yes.
Okay. All right. So here is what we need to do. We need to find where these curves intersect. Now I was typing something and maybe you could see it, maybe you can't, but now you can. And now I'm going to use the chalk. So that means we're going to say, when does the square root of x equal x squared? And by the way, you see we're taking the square root of x, so we know that x has to be bigger than or equal to 0 because you can't take the square root of x without that. So we're saying x squared is bigger than or equal to 0. So what I would do then is here I would square both sides. So when I square this side, I get that. When I square x squared, I get x to the 4th. But I still need to solve this. So this means that x to the 4th minus x is equal to 0. Okay, now if you want to solve that, the way to solve that is to factor. So we set x, and then this is going to be x cubed minus 1 is equal to 0. So two things being equal, the two things being multiplied together equaling 0 means that one of them is equal to 0. So either x equals 0, that's what I get from the first term, or x cubed is equal to 1, but that says that x is equal to 1. So now we know that x goes from 0 to 1. And that was what I was talking about. Now we did this the similar step in a problem last time, but you know, I hope this answered. Well, okay. Are your questions answered? And again, I'm talking to the student who was posing the question.
Yeah, I just forgot that you're supposed to set them equal to each other. Thank you.
Okay. And I mean, we have this, but maybe there was more too. But anyway, if you have additional questions, please ask them. I'm starting my count again, and I'm trying to share a different screen with you. So let's see. I guess it is this one that that I'm sharing. And I'll share it as this, and then I'll hide the sharing bar. Okay, I'm starting my count again. Okay, I reached 10 Mississippi, so we're going to call that good. So we're moving on to what I'm calling example 4, and I will read it for you. Find the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared plus 1, y equals 0, x equals 0, and x equals 1. But this time we're revolving them about the y-axis. This may have been the first example where we're revolving it around the y-axis. So the very first step is you want to sketch a graph of what this is all about. Okay, so here is what we have. The graph of y equal x squared looks like this. Or excuse me, the graph of y equal x squared plus 1 looks like this. It is this black curve. And the other graph that we have is y equals 0, x equals 0. Well, y equals 0 is the y-axis, or excuse me, y equals 0 is the x-axis, and x equals 0 is the y-axis. And they also told us, hold on, x equal 1, and so x equal 1 is out here. So you see the region that we're revolving then is going to be the area that is colored sort of blue here. Now we have a couple of slices that we've made, but it is the area that is colored blue. But we're taking this around the y-axis. So you see this little going around thing is talking about the y-axis, not the x-axis, not y equal 1. I think it's the first time we went along this way. Now, this is where it's important. And again, there are different ways to do this problem, and we will learn different ways to do this problem. But so far, the only thing that we have studied is the disk and the washer method. And again, I'm saying something that I put in red before. It is important that when you're doing the disk or the washer method, you draw your slices perpendicular to the axis of revolution. So the axis of revolution is the y-axis. So I'm drawing my slices this way. That means these are the delta y's, and that means that it's going to be dy. So we're integrating dy. Okay. Another thing to observe, though, is since I'm integrating dy, when I'm going from 0 to 1, the function on the left side is going to be x equal 0. And the function on the right is going to be x equal 1. Okay, so those are constants. So this really is going to be, just a square, and I can compute this using integrals, or I can just use a geometry formula. But look what happens when I go from 1 to 2. And when I go from 1 to 2, and by the way, going back to the discussion I had with the student on the last problem, you do have to figure out that this point is 1, 2. But anyway, we have this, but between y equal 1 and y equal 2, the function that's on the top is still x equal 1. But the function that's on the bottom is this one, which was y is equal to x squared plus 1. But I want this to be y. So you see y equal x squared plus 1. I have to solve that for y because I'm integrating dy. So if y equal x squared plus 1, x is equal to the square root of y minus 1. So you see what we're learning here is for y between 0 and 1, the inner radius is the inner number is 0, and this radius is 1. But between 1 and 2, we're still 1 over here, but the inner radius, this one, it becomes a washer. This is the square root of y minus 1. Now, and when you rotate this thing around, what you get is a thing like this, and this could be a container for a potted plant or an ashtray or something. So anyway, this is what you get when you rotate it. So the pictures are very important to understand this. And because the definition of what was inside and outside changed, we have to have two integrals to evaluate this. Okay. So the volume is going to be these two integrals. So it's going to be the lower square. So this is going to be the volume is equal to pi. This is going to be the integral from 0 to 1 of the outer radius squared, which is 1 squared, minus the inner radius squared, which is 0. That's just going to be 1, but we'll do that in a moment. But here we have to use the washer formula. So this is again pi, but now we're integrating y going from 1 to 2. This is dy, of course. Now the outer radius is 1 squared, but the inner radius as a function of y is the square root of y minus 1 whole squared. Okay, and so that's the setup of the integrals. Now we need to compute these integrals in order to finish the problem. So this is pi times the integral from 0 to 1 of 1. Now 1 is y to the 0, so you add 1 to the exponent divided by this is just y. That ends up being 1, so I just get a pi there. Now I go over to this one. The pi just sits there on the outside. When I integrate 2, y to the 0, the 2 just sits there, but this is y to the 1 over 1. So that is 2y. This minus sign is that minus sign. And then I'm integrating y. Again, the pi is still times that, but I add 1 to the exponent, divide by the new exponent. This is y squared over 2. And then I plug in 2 and 1 here, and 1 and 0 here. Now I talked about getting pi here. But here, when I plug these in carefully, and again, you have to do these things without a calculator, it's going to be pi. This is going to be 4 minus 2 minus 2. Those actually cancel out. And so you get pi over 1/2 pi. 1/2 pi and pi is 3/2 pi. And so that's what we have for the answer to this problem. Now, this was, in a couple of ways, maybe more involved. So I'm going to be pausing and counting to 10 Mississippis to, and I'm inviting your questions on this problem. Okay, your questions are, of course, always welcome, but I reached 10, so we're going to move on to the next example. This is a very realistic example, and again, I erased some things here, and I erased some things because the expectation on a high stakes assessment or even on a low stakes assessment is that you can draw the picture yourself. But I will read this example 5 for you. So a manufacturer drills a hole through the center of a metal sphere, and the metal sphere has a radius of 5 inches, and the hole has a radius of 3 inches. And so the question is, what's the volume of the resulting metal ring? And so let's look at a picture, which is the first thing that you want to do. Okay, so here is your, now, and here's something that does happen in this problem. Nobody told you a coordinate system, so you're an engineer trying to solve this problem. So what you're going to want to do is you're going to want to set up a coordinate system. Now, some of this stuff ends up being tradecraft, and you just learn by doing things, but you need a coordinate system in order to deal with this. So what we're going to do is we're going to say that the center of this sphere is at 0, 0, 0. And I gave you 3 coordinates because there's an x coordinate, a y coordinate, and a z coordinate. Okay, so the center is 0, 0, 0. But what happens here in the plane, and what you're doing is, you see, you're taking something and you're rotating around now the x-axis. Now there's some axis, but that's when the z is equal to 0. And so what you have is you have coordinate system. You have to think about that. So we're rotating around the x-axis, and here is the outer piece of the sphere. So this is going to be, if z is equal to 0, you have, and if the radius, so it's going to be x squared plus y squared equal 25 in my situation, because that is a circle in the xy plane. So you see, that's the piece that you're taking around. Now here is where you cut out the cylinder from the middle. And you see on this end, you have a circle of radius 3. And on the other end, you have a circle of radius 3, but then you have the length goes from one end of the circle to the other. But you have to figure out what are these points when y equal 3. You see, this boundary is going to be y equal 3. So what you're rotating around the x-axis in this picture is this piece of real estate. It is going around, and that is forming the volume of this. Okay, so we have to figure out, one thing we have to figure out is when y equal 3, what is x? Well, let's think about that. When y is 3, if I were to put 3 here, this would be 25 minus, or I put 3 here. So if I square both sides, what I would get is 9 is equal to 25 minus x squared. So x would be plus or minus 4. So you see, we figure out that these are plus or minus 4. We're taking this piece around this axis. So the inner radius is 3, and the outer radius is r of x, is the square root of 25 minus x squared. Now we're going to see some words that talk about that. So here we go. You can imagine that the ring to be generated by a segment of the circle whose equation is x squared plus y squared equals 25. And we figure out what x is because we know that x squared plus y squared equals 25. And we're putting y to be 3. So x squared is equal to 16, or x is equal to plus or minus 4. So the inner radius is 3. The outer radius is on that circle, which is the square root of 25 minus x squared. So we have a volume, a formula for the volume, and this is a washer method. So the volume is equal to pi times the integral from a to b. This is outer radius whole squared minus inner radius whole squared. Now I start substituting things in. We know that x runs from minus 4 to 4. And we know that capital R of x was the circle, so that's the square root of 25 minus x squared whole squared. This minus sign is that minus sign, and R of x was 3 all the way through. So that is 3 squared. So this is going to then be equal to pi. And when I square 25 minus x squared, the square root of that, I just get 25 minus x squared. So 25 minus x squared minus 9 is 16 minus x squared. And again, I'm integrating dx because that's the way I drew my slice. So I'm going to have the pi just sits out here. This is 16x to the 0. I add 1 to the exponent, divide by the new exponent, that is 16x. Minus, and here I add 1 to the exponent, divide by the new exponent. This is x cubed over 3. I have to plug the numbers in, and I have to be a little bit careful because you see when you're plugging in a minus 4 cubed is minus 64. So you have to be a little bit careful with that, but you have pi times 256 over 3. Okay, so I'm going to count to 10 in case there's questions on this example. Nicole, are you guys still out there?
Yeah.
Okay. People are just not having questions, so I don't know. I don't know what that means, but anyway, your questions are always welcome, so please feel free to ask them. Okay, now we move into the last topic for this lecture, and this is talking about solids with known cross sections. And this has to do a lot with the using the integral to get areas by accumulation that I talked about at the very end of last period with you. Okay, so here we go. So with the disk method, you can find the volume of a solid having a circular cross-section whose area is A equals pi, and this is capital R squared. Now, this method of finding these cross-sections can be generalized to solids of any shape, as long as you know a formula for the area of an arbitrary cross-section. So there's a whole bunch of formulas that you know from your pre-calculus about areas of squares, areas of rectangles, areas of triangles of various kinds, areas of semicircles and trapezoids, and it could go dot, dot, dot. It goes on and on and on. And so what this means is that if the solids, if you know about the cross sections, the volume is just going to be the integral from A to B of whatever the area of that cross section is. Now I'm going to show you an example. I'm going to come back to this formula, but I'm going to look over here. And suppose that we were talking about taking squares, and I think we're going to pretend that this is a square, cross sections that are perpendicular to the x-axis. So you see, we are talking about a three-dimensional figure, but it is composed in the following way. We have cross sections. So anytime we cut a cross section perpendicular to the x-axis, we get, in this case, it looks to me like it is a square. Okay. But what happens is this square could be different than the next square and the next square because this function is curving. Okay, so these are squares that are perpendicular, but we know the formula for the area of a square. Similarly, we could say, oh, let's have cross sections that are perpendicular to the y-axis that are squares. So you see here I get a square, and this is a square that is perpendicular to the y-axis. But this square is different than the square out here, is different than the square going in there. So you see these are always changing. So we're going to integrate the function that tells us these areas. Okay, so for cross sections of area A of x, taken perpendicular to the x-axis, when we're taking perpendicular to the x-axis, we're going to be integrating dx. So that means we're integrating from A to B the formula of ax. Now this is just like when it was a circle, we said, oh, this is pi r squared dx. But now we have a different area function. And for cross sections of area taken perpendicular to the y-axis, again, you're perpendicular to y-axis, so this is dy, but you have this formula. Okay, so again, these are some more formulas that you want to commit to memory. Now, we're going to do a problem with this, though, and so we're going to do this example. The cross sections perpendicular to the x-axis are equilateral triangles. Now, you want to remember what an equilateral triangle is, and I think I'm going to pause just for a minute. And I'm going to go here, and I'm going to go to the blank whiteboard. And I'm going to draw, at least I'm going to try to draw an equilateral triangle. It won't be perfect, but there is one. Oh, that says, I don't know if I can duplicate that. Let me try something. I'm experimenting. That didn't work. So I'm just going to continue faking it. So there's one piece of the triangle. There's another piece of the triangle. And the third piece of the triangle will be joining these two. And I think I can do better than that. Let's see, is there an eraser up here? Yeah, there's an eraser. Let me see if I can just erase that last one. This is the one I didn't like. So I'm going to draw a better one. So this is like this. All right, so you're to pretend that this is an equilateral triangle, which means that all of those sides are equal. Okay, now we're going to talk about what is the area of an equilateral triangle, because you see we need to know how to do that. So what I'm going to do is I'm going to, let's see. I think I don't want to do that. I'm just going to write some things here. So the area of an equilateral triangle, actually I'm going to say an area of a triangle is 1/2 a base, in fact I'll type base, times the height to that base. Okay, so the area of a triangle is 1/2 the base times the height to that base. So for this equilateral triangle, then, what I'm going to do is I'm going to, does this let me do a dotted line? Maybe not. Okay, that's all right. I'm going to do a dotted line here. So what I'm doing is trying to draw a dotted line. And I'm going to erase this because I'm unhappy with how that's working. Okay, I'm trying to call up the eraser and erase those, and I'm not getting it done, so I'm just going to draw here. All right, so I'm dropping the perpendicular there. Now, each angle of a equilateral triangle is 60 degrees. So this is 60 degrees. And so this is 60 degrees. And this is bisected, so this is 30. And this is a 90-degree angle. So that means if I call this side S, and I call this side S, then the entire triangle, every side is S, but it's a theorem you know from geometry that this is this side down here. Well, this side down here is also going to be S. So I'll try that again. S. There we go. Okay, so all three of those sides are S, but this was a 60-degree angle. So you see, this is 1/2 the base times the height. So I need to know what is this height in order to know the area of an equilateral triangle. Well, we have some trigonometry going for us here, and that is good. You see, this angle is 60 degrees. And so H is equal to S times the cosine, or excuse me, the sine of 60 degrees. And the sine of 60 degrees is the square root of 3 over 2. So you see this H from triangles that you know about, and that's a 30, 60, 90 right triangle. And so this is S times the square root of 3 over 2. Now we actually need this in order to answer the questions. And so we're now going back, but please make note of this. In fact, I guess what I will do is I will try to cut this and maybe save it. Let's see, that didn't work, so I'm going to try it again. Okay. All right, so I have that, and I'm going to make a chart out of that. And I'm going to go back and do some things. Okay, so it is there. And so now I'm going to change what I'm sharing with you. So I'm going to stop sharing this. I'm going to go back to my application screen. And we will share that. And so now, Nicole, you should be seeing a PowerPoint slide. Is that what you're seeing?
Yes.
Great. Okay. And everybody hang in there. I know some people just left, but I will be dismissing you in about 10 minutes. We're going to finish this problem. Okay. So you see, we need to understand this. And so the area of a triangle is 1/2 the base times the height. But the base of the solid of the region is bounded by the lines this. So remember, you see the cross sections perpendicular to the x-axis are equilateral triangles, but the base of the solid, the base of the triangle, is bounded by these two lines, and x equals 0. So let's look at a picture of what this looks like. So you see, here is the equilateral triangle. And this equilateral triangle is different from this equilateral triangle. It's different from this equilateral triangle. But they're all equilateral triangles because the cross sections are equilateral triangles. And let's look at what these actually look like. So the cross sections are equilateral triangles. But here is what f of x is. Here's what g of x is. So you see, when we're drawing the base of those triangles, and again, it's perpendicular to the x-axis, so the base of those triangles is this slice that we see right here. So that means the other two sides are the same as the distance between these. So you see, we can use the formula for the area of the triangle, and we know one of the sides. So if we go then to the next slide, we get this. So the base is equal to f of x minus g of x. Now look what happens when you do this. 1 minus a minus 1 is 1 plus 1 is 2. And here I have minus x over 2, but this is minus a minus x over 2. X over 2 minus that. So minus 1/2 x and another minus 1/2 x is this. So the length of the base is 2 minus x. Now, so it's 1/2 the base times the height. But you see the height was the square root of 3 over 2 times the base. So if I square that, I get the square root of 3 over 4. And this base is 2 minus x whole squared. So you see, this is the area of the cross section of an equilateral triangle. Okay, now because the x ranges from 0 to 2, we just are integrating that. Now to do this, you can use a u substitution. You can't, so this square root of 3 over 4 just comes out. But if you do a u substitution where this is 2 minus x, you get a minus sign that happens here. So we're going to plug in 2 and 0, and we get 2 square root of 3 over 3. So you see, now we've talked about these uniform cross sections as well. So I want to pause. I'm going to count to 10. Mississippi, to see if people have questions on this example.
Yeah, I have a question. Why are we squaring?
Please go ahead. Just go ahead.
Yeah, okay. Why are we squaring rather than having to get the area?
Okay, I'm going back to my blackboard to answer that question, okay? Now my blackboard probably isn't there exactly the same way, but that's okay. So I will get it back. So I am stopping sharing what I'm sharing. I'm going back to this thing and I'm going to do the blackboard again. And Nicole, and I'm going to erase all this stuff, okay? Now what we know is that H is equal to the square root of 3 over 2 times the base. And I want to talk to the student who asked the question. You remember this formula now, yes?
Yeah.
Okay, so this is going to be 1/2 the base times the height. But the height is the square root of 3 over 2 times the base. So this is going to be 2 times 2 is 4. Root 3 times 1 is root 3. And this is base squared because it's base times base. So on that chart that I had, then the thing we were integrating was the constant, the square root of 3 over 4 times the base, and the base in our problem was 2 minus x whole squared. Now I'm going to pause for a minute because I think I may have answered your question. I actually hope I did, but I'm I'm more than happy to talk some more if that wasn't enough.
Yeah, no, that makes a lot more sense now. Appreciate it.
Okay, good. Okay, so that is that's what happened with that problem. Okay, so that is good. Now I do want you to get your money's worth, so we are going to work till 1:15, and I have some more examples for you to go through. So that's all fine. Okay, let's look at the next example, which I'm sure is going to be the last example of the day. And I think I screwed up because I didn't stop sharing the other things. So I have to go back to Blackboard and I have to change the sharing. So now I'm sharing you an application screen. And what you're going to be looking at, I hope, Nicole, is a PowerPoint slide that says example 7.
Yeah, I see that.
Okay, good. Now what we're supposed to do here in this example 7 is prove that the volume of a pyramid with a square base is V is equal to 1/3 the height times the base, where this is the area of the base. So V is the area of the base. Okay, so what we're going to do then is we need to turn this into one of these problems that we're talking about. And you see, if you have a pyramid, and this is a pyramid, we talk about, well, what is the cross section? Well, anytime you make a cross section here, what happens is you get a rectangle. Okay, because if you think about being parallel to the the plane down here of y equals 0, you can see that whenever you're making these cross sections, you will get an a of x. And so this is an a of x. Now, here is something that's, you have to think about this, but this is thinking that we have to do. The area of the base is b, but this is b times b because this is a square pyramid. So we have this. But now we have to say, well, what happens with this as you go up? Well, as you go up, if you think about this, there are triangles here, and the triangles look like this. So if we start down here at y equals 0, and we go up to a point that we're just going to call y, then we call this y. But if the height of the pyramid is h, then what we're having is we're getting, this is y, but this part is h minus y. So if we use the formula for the area of a triangle again, we get that the area of this rectangle, which is adding a couple of the triangles together, is going to be b squared over h squared times h minus y whole squared. So that is the area of the triangle that you have there, and that can be changed into the area this. So what we get then is we're going to integrate this from the bottom, where y is equal to 0, to the top, where y is equal to h, and this is a of y, and this is dy. So we substitute the equation that we find for a of y. It is this. Now b squared over h is just a constant, so I can jerk it through the integral sign. This is the integral from 0 to h. I'm integrating this y. So you have to do a u substitution here, and the u substitution is where you get this minus sign, but you add 1 to the exponent and divide by the new exponent. Now when I put h in here, I get 0. But when I put 0 in here for y, I get h. And so this is going to be h cubed over h squared. This is b squared over 3. So you see this is 1/3 h, and then this is b squared, which was the capital B. And so you see we've proven a geometry formula using this technique. Okay, now, so what we've done, and just giving you a little bit of breadcrumbs, and breadcrumbs meaning to guide you, we've now done section 6.1 in your textbook. There's some homework there. I'm going to be posting the next 2 videos probably later tonight. I'm not really free again, because I'm teaching again, until probably a little past 7, but I will be posting these. You have your books to read, you have homework problems to read, and that's what's in front of you. Now I have, and so anyway, I guess I'm saying, I guess I'm going to pause and just ask if there's any questions. Otherwise, I'm going to count to 5, and if there's questions, I'll entertain them. Otherwise, I will stop the recording. Okay, so I am stopping.